So for the test, I should have just made it so you can look at your test about 45 minutes ago. Um, so uh, the yeah, you should be able to look at your answers. And I'm gonna do what I did for test two, in that I'm gonna make a separate video that just goes over all the answers for test three. And so you can just watch that in case you got like something wrong. That will show you how to do how to do it correctly for the final. As always, if you have questions on how I scored something for test three, once that video is out and you look at what you did compared to what I did, feel free to shoot me an email and we can hash that out. Otherwise, let's get right into it. And today we are going to continue our discussion on quantum mechanics. And we're going to look at where electrons are around the atom still. All right. So the first thing we're going to talk about are our orbital diagrams. And we kind of already mentioned this on Monday. We were looking at, those dashes, and we're looking at our different energy levels, 1s, 2s, 2p, and all that. But what this slide is telling us is how we can relate electron to our dashes. So for any electron, every electron inside the atom gets a set of quantum numbers associated to it. And we already talked about three of those numbers, N, L, and M sub L. The last quantum number that we haven't talked about yet is called M sub S, also called the spin. And there's only two spins, spin up or spin down. They get numbers of plus 1/2, and this says minus 1/2 on the bottom. Not that important to know plus 1/2, minus 1/2. Just need to know there are two different values. Now, like I said, any electron can only have a unique set of quantum numbers, right? So you get 4 quantum numbers, but no two electrons can have the same quantum numbers. It's like their personal ID code, right? In a specific atom, only one electron can have a specific ID. So when we are looking at our energy levels that we talked about on Monday, if we look at the 1s orbital, remember, if we're talking about 1s, n equals 1, and s means that L equals 0, right? That's what 1s means. If L equals 0, m's of L can only equal one value. That's 0 as well. Remember, just as a reminder, m's of L, that quantum number goes from minus L all the way to positive L, counting 0. Well, if L is 0, you only have one value, 0. Now these dashes, and some people also put them as boxes, this is where we can put electrons. Now, we can only put 2 electrons per box. And the reason for that is what I was talking about, which is called the Pauli exclusion principle. No 2 electrons in the atom can have the same 4 quantum numbers. So if we look at the orbital diagram I just drew, and is also drawn at the bottom of the screen there, I can list these quantum numbers, which is actually done on the right-hand side right here. So this up pointing arrow has quantum numbers 1, 0, 0, plus 1. This down pointing arrow or electron rather, has quantum numbers of 1, 0, 0, minus 1/2. Again, all this is saying, just I will summarize it again in like 2 to 3 sentences. Every electron in the atom must have a unique set of quantum numbers. And in every like m's of L value, so every m's of L value, you can have 2 electrons. That's because your electron can be spin up or your electron can be spin down. When we have our whole energy diagram, which is being shown here, we have certain rules that we have to follow to put electrons in. So just to get you oriented with what you're looking at, each dash here is a place we can put electrons. So again, I'll just label out the quantum numbers for the first 3. So 1s is n equals 1, L equals 0, m's of L equals 0. 2s is n equals 2, L equals 0. This is m's of L equals 0. 2p, n equals 2, L equals 1. Then m's of L can be minus 1, 0, or plus 1. That's why we have 3 dashes for the p orbital. Now, when we put electrons in, these blue arrows are our electrons. Our rules we have to follow are this one. First, we have the off-ball principle. Any of you who speak German, apparently off-ball means off-bow, probably, means to build up. So what that is that you start from the lowest energy first and you just move up. So 1s is the lowest energy, so we have to put electrons in it first, followed by the 2s, then 2p, 3s, 3p, 4s, so on and so forth. So you fill it from the bottom to the top. And our next is the Pauli exclusion principle. Basically what we just talked about on the previous slide, for every dash, you can only have 2 electrons. So for every m's of L value, you can only ever have 2 electrons. And then Hund's rule is, which is shown in these 2p orbitals, when filling electrons, fill in the empty m's of L values first before you pair electrons. I'll repeat that. Hund's rule says, fill in empty m's of L values first before you pair up electrons. Hund's rule is always described with seats on a bus, right? If you get on a bus and you don't know anyone there, you are going to probably take an empty seat before you sit next to a stranger. Same thing with electrons. If an electron needs to be put in the 2p energy level, it's going to look for an empty m's of L value before it pairs up with another electron. That's why in our diagram here, where we have 4 electrons in the 2p orbital, we have each orbital filled up once before we pair our electrons. So that's how you would distribute 4 electrons. All right, I know that was a lot of information right there, a lot of new concepts. So any questions right off the bat about anything that I've mentioned so far? All right, if not, we will move on. So the first thing we're going to do is we're going to learn how to read the periodic table and determine an electron configuration. That is, we're going to determine what energy levels we have, what orbitals we have, and how many electrons are in each orbital. So I'm going to do A and B for us, and then I'll let you loose on C, D, E, and F so you can get your feet wet. So the way to do this I want to do A. I want to find the electron configuration for carbon. The first thing I do is I find carbon on the periodic table, and carbon is element 6. Okay, and the way to label this electron configuration is that you start all the way with hydrogen over here. Hydrogen is in the first row. That's what that 1 means. And it's in the S block. The brownish color right here are S block orbitals, and helium is also in the S block, even though it's all the way over here. Heliums are one outlier. So the way to start writing down the electron configuration is that you start at hydrogen and you just count. So hydrogen's my first element, so that's 1s1, 1s for what the block I'm in. Helium is my second element in the 1s block. That's 1s2, right? So my electron configuration for carbon to begin with is 1s2. My goal when I'm doing this is I'm going to keep counting like this until I get to carbon. So hydrogen is 1s1, helium's 1s2. I'm not at carbon yet, so I write down where I've gotten so far in the periodic table. Next, I move over to lithium. Lithium, second row, S block. So this is 2s, and it's the first element in the 2s block. So this is 2s1. Barium is 2s2. I'm not at carbon yet, and I'm going to leave the S block, so I'm going to write down where I'm at. So this is 2s2. Now move over to boron. Boron's in the second row, but now in the P block. So all of this green is the P block. Boron is the first element in the P block, so it's 2p1. And then we're finally at carbon. Carbon is the second element in the P block, so we call this 2p2. I'm at carbon, so I'm done with writing my electron configuration or getting to my electron configuration, so I need to write it down. And what these are telling us, again, is the number in front tells us the energy level, so that's N. The letter is angular momentum, that's L. These numbers up here are the number of electrons. So what this electron configuration is telling us is that we have 2 electrons in the 1s orbital. We have 2 electrons in the 2s orbital, and we have 2 electrons in the 2p orbital. So that is the full electron configuration for carbon. 1s1, 2s2, 2p6. Now let me do, well, before I do AS, are there questions about how I got carbon? How I knew carbon's 1s2, 2s2, 2p2. If not, let me do AS. AS, where are you again, AS? AS is element 33. There you go. I think I said 2p2. If I said 2p6, that was a mistake. It should be 2p2. Okay, let's do AS. So AS is element 33. And I'm going to do the same thing. Start at hydrogen and work your way over to element 33. So hydrogen's 1s1, helium's 1s2. I'm about to leave the 1s block. I'm not there yet, so I write that down, 1s2. Move over to lithium. Lithium, 2s1. Barium, 2s2. I'm about to leave the S block again, and I'm not to AS, so I write that down, 2s2. P block. Barium is 2p1, carbon 2p2, nitrogen. Let me change this so you can I think, yeah. So nitrogen 2p3, 2p4 for oxygen, 2p5 for fluorine, 2p6 for neon. again, I am not out of, or I'm about to leave the P block and I'm not to AS yet. So I want to write down my progress so far. So right now I'm at 2p6. Then I go back over. Now I'm at the third row S block. So sodium is 3s1. Magnesium is 3s2. I'm not to AS yet, but I'm about to leave the S block. So I write that down, 3s2. Then I go all the way over to the P block again. Aluminum, silicon, P, phosphorus, sulfur, chlorine, argon. I haven't hit the AS yet. So argon is 3p6. So 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Not there yet. So I'm going to write down 3p6. Go back to the S block. Hopefully doing this long one is making you see what's going on here. Potassium, 4s1, 4s2 for calcium. Not there yet. And this is the only tricky part about it. Anytime you get to the D block, the column or the number for the D block is the row number minus 1, right? So for the D block, when we start in SC, we're in row 4, but this is called 3D1. Again, D block is you take your row number minus 1. So here, 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, zinc, 3D10, not to AS yet, so we're going to write down 3D10. And then finally, we're going to get the AS. Once we're back in the P block, we go back to normal numbering. So 4s1, 4s2, 4s3. We're at AS. And we're done. So 4p3, not S, 4p3. And so our complete electron configuration for AS is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. And that information is all given in the periodic table as long as we know how to read the periodic table. All right. With that, if you have questions about that, please do ask. But now is the time to take what you just saw and see if you can apply it to P, R, E, N, A, and Y now. So see if you can do C, D, E, and F and figure out what the electron configurations are for those problems. So 6D is as high as the chart goes? Yes. And we didn't talk about the F block. Don't worry about the F block. Right now, all we're worried about is the D block and the P block. But yeah, like once you get into like 6D, like 5F, things get really weird there. So we're just going to focus on the basics. And as always, if you want to check your answer, once you have one, feel free to send me a private message and I can just give you a yay or nay for that. I'll give people like 2 more minutes or so to try and get all 3 of these or 4 of these finished, especially Y, as that goes into the D block. So really want you to practice these skills. All right, let me start doing some of these in case you are lost. So phosphorus element 15. So to get there, we need to go through 1s2, 2s2, 2p6, 3s2, and then we'll finally end up at 3p3. For 1, 2, 3. Argon, it's just 3 spots over. So if we continued from phosphorus, it would be 3p6 because we have to count 6 times to get to argon. So it's the same thing, just 3p6. So 1s2, 2s2, 2p6, 3s2, 3p6. And then for sodium, well, sodium is before all of this. So it's number 11. So to count to sodium, it's 1s2, 2s2, 2p6, and then we stop at the 3s1, right? It's the first element in the 3s block. And then for your tritium, which is Y, your tritium is all the way down here in element 39. So your tritium, we have to do a lot of counting here. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then remember, when we hit the D block, it's the row minus 1. So 3d10, not quite there yet. We still have to keep counting. 4p6, 5s2, and finally we get to your tritium. It's in the 4, remember, 5 minus 1 is 4. D block, so 4d and then 1. So that is the complete electron configuration for your tritium. It's the first element of the D block in the 5 minus 1 row, because that's what the D block goes by, row number minus 1. All right, now that you've seen how to use the periodic table to determine full electron configurations, are there any questions of how I was able to figure all of this out? Is there a shorter way to write it? We will be learning about that next. Yes, there is. You learned something new today? That is the hope. Yes. So writing all that out, long form, takes forever. So there's a different way to do it. So this is the shorthand way to do it is you just name, if an element comes after a noble gas, and remember the noble gases are the very far right column. So here are our noble gases, Ng for noble gases, right? So if your element comes after a noble gas, you can just put the noble gas in brackets. And what that is saying is that my element has the electron configuration of this noble gas plus all this other stuff after it. So question 2, and hopefully you have your own periodic table available because I did not provide one on this slide for some reason, is we're going to use the periodic table to determine which elements we're looking at. So here we have argon 4s2, 3d10, 4p6. So let's go back to the periodic table and try to figure that out. So I'm going to rewrite that for us. So we have argon. Actually, I think I have all of them written down, so I'll just do that. Argon 4s2, 3d10, 4p6. 6. So the shorthand is, okay, we start at argon because that's what we're saying we're at. Then we go 4s2, 3d10, 4p6. So 1, 2, 3, 4, 5, 6. The element is krypton. So krypton has the electron configuration of argon 4s2, 3d10, and 4p6. What you can also do for krypton is, because it's a noble gas, krypton, you could just put krypton too. So noble gases, anytime you have a noble gas or any element that follows a noble gas, you can just use shorthand and say the electron configuration is noble gas plus all this other nonsense. So I'll just rewrite what we're looking at for question 2. So we can have the periodic table here. So B is argon 4s2, 3d2. C is krypton 5s2, 4d10, 5p2. And then D is krypton 5s2. Tell me what elements correspond to that electron configuration, those electron configurations. Why did I pick argon? Well, if I'm talking about krypton, argon is the noble gas that directly follow or is before krypton. You always want to pick the noble gas that is before your element. So if I was doing potassium, right, I would always pick argon. I would never say neon because then I just have other stuff to write. So for potassium, I can just write argon 4s1 because potassium's after argon. You just pick the noble gas that you passed most recently on the periodic table, I guess is how I would put that. So everybody take a minute or two to try and figure these ones out. Okay, so if we look at this, start at argon. So for B, start at argon and then go to 4s2, 3d10. Or sorry, I wrote D32. Huh, that's weird. Should have been 3d2. So 3d2, so 1, 2, that would be titanium. C, start at krypton, go 5s2, 4d10, all the way to 5p2. 5p2 is Sn, tin. And then Kr, krypton, just 5s2, Sr would be strontium, Sr. All right. Any questions about the shorthand way to write electron configurations? And I'll say right now on a test, I would accept either form unless I specifically ask. If I specifically ask for full, that means like write out everything, like 1s2, 2s2. If I just say electron configuration, so without the full, you can write it either way. So the only time I would want like 1s2, 2s2 all the way is if I specifically say what's the full electron configuration. But generally, people will always use this shorthand. Okay, so any questions? If not, we can move on. All right. So we're going to just continue working on this. I want you to use the periodic table now to tell me how many electrons are in the 3s orbital of Mg and so on and so forth. So I'll do A for us, so we can just see. A is number of electrons of 3s and Mg. Well, if we go to Mg, the electron configuration of Mg is neon 3s2. And remember, this number tells us how many electrons are in that orbital. So magnesium is 3s2. That means it has 2 electrons in the 3s orbital. All right. Take a minute with your periodic table. Hopefully you have one. If not, like pull one up on your phone or on the internet and tell me electrons, 3d electrons in nickel, 4d electrons in Tc, and 6p electrons in lead. So nickel, I believe, doing this blind without the periodic table in front of me, should be a electron for 3D. Let me just pull up my periodic table so I can just double check myself as I go. Yep, so nickel should be 8. Tc, the number of 4d electrons in Tc, 1, 2, 3, 4, 5 should be 5. Because it is the 5th element in the D block. And then for lead, lead is the 2nd element in the 6p block, so it gets 2 electrons. Any questions about how to determine the number of electrons in each block? All right. So I'm hoping you're all liking this non-math portion of general chemistry, because it is now over. So we do have a way to actually calculate how different charged particles interact with what energy they interact with. And so our equation is, sorry, there's a question, is lead, xenon 6s2, 3d10, 6p2. Let me double check that. 6s2, it's 5d10, right? Because it's in the 6th row. So the D block is row -1. So 6s2, 5d10, 6p2. All right. So going back to what I was saying, Coulomb's law allows us to determine the energy of interaction between charged particles. Now, in general, in like chemistry, biochemistry, basically any chemistry, any hard science, for energy, negative energy is usually a good thing. That's supposed to be a check mark. Positive energy is usually a bad thing. Maybe the way you can keep that in mind is if you turn a positive on its side, it looks like an X. An X is bad. So negative energy is good. Positive energy is bad. Negative energies come towards each other. Positive energies repel each other. And so the way to calculate the energy of interaction between charged particles is Coulomb's law. Coulomb's law is up here in the top, which is 1 divided by 4 pi dielectric constant, so epsilon naught, multiplied by charge 1, charge 2, divided by distance. So a couple of things to say about this equation. What is a dielectric constant? I'm sure you've not heard of that term before. Maybe, maybe not. A dielectric constant is, to put it simply, how well you screen charges. How well you screen charges. And by screen, I mean like hide charges from each other. So a vacuum has the worst dielectric constant there is. A vacuum has a dielectric constant of 1. Basically, what that means is no matter how far I put 2 charged particles in the vacuum, they always know they exist. They can feel each other because there's nothing in between them that blocks them. So if I take a proton and an electron and I put them 2 miles apart in a vacuum, they're just going to fly towards each other because they know each other exist. While water has a very high dielectric constant, 72. You don't have to remember these numbers. What that means is that ions in water don't know each other exist. So if I take a positive charge and a minus charge, and I put them like 30 nanometers away, which is really far actually, they would not know they existed at all because all that water would be in the way that would screen or hide their charges. So that's what a dielectric constant is. So that being said, for our purposes, we can ignore that part of Coulomb's law, because when we are going to be looking at the charge interactions, we're always going to be like in water for general chemistry, or at least we're always going to be in the same media. We're not going to say what's the charge of 2 charged particles in water versus oil. I'm never going to give you something like that. So the epsilon is a constant, so I don't need you to worry about it. What we do need to understand is this second part of Coulomb's law. Q1 multiplied by Q2 divided by R. So these Q's just mean charges. So what is the charge of atom 1? So charge of atom 1 is Q1. Q2 is what is the charge on atom 2. R is distance between atoms. So that's what Coulomb's law states. What did I say screen meant? Screen is hiding charges. So if I have 2 charged particles, the better you are at screening them, they won't be able to see each other, right? Or another way is you're good at hiding charges almost. All right, so Coulomb's law for us basically is charge of particle 1 multiplied by charge of particle 2 divided by the distance between the charged particles. That will tell us energy of interaction for these atoms. So here's our last question for the day, and I do have a poll for this actually. So according to Coulomb's law, and you actually don't need to do any math for this if you can figure out how the equation works. So you don't need a calculator. You can use a calculator, but you don't need one. Tell me which charged particles has the lowest potential energy. And when I say lowest potential energy, that means most negative. So what has the most negative energy here? And let me get that poll up. So tell me, what do you think has the lowest or most negative potential energy? Again, the best way to do this is to look at the equation and try to puzzle it out. But if need be, feel free to use your calculator and calculate every single one. And I'll give people like a minute or so, maybe like 45 seconds. And after that, I'll show you the really fast way to do this. I'll show you how to logic this out without needing a calculator. Right, and the poll, let's share it. And the majority of you got it right, that it is B that has the most negative energy. I'll show you how to do this. I'll show you the logic, my thought process of how to do this with 0 calculations, because I set up this problem to need 0 calculations. First off, what do you need to have a negative energy? Well, you need your charges to be opposite, right? Because if I'm ignoring this first part, it's just charge atom 1 multiplied by charge of atom 2 divided by distance. Distance between 2 objects can't be negative. Like I can't stand minus 10 feet away from you. I can only stand 10 feet away from you. So the only way for this equation to be negative is if one atom is negative and one atom is positive. Therefore, we can eliminate option 3. Option 3 has charges that are the same, so that can never be negative. All right. Now we have to do distance, right? We are dividing this by distance. Things that have a shorter distance will have a more negative energy, right? Because for D, right, my R is 200, so my denominator is 200. For A, my denominator is 100, and if we compare A and D, they have the same numerator, right? So D I can eliminate already because I'm looking at the same charges, but for their distance, so that can't be more negative. So by process of elimination, I'm now down to A and B. A and B separated by the same distance, but B has a bigger positive charge. So really my math is, if you want to look at the math of it, it's 1 times -1 divided by 100, that's A. B is 2 times -1 divided by 100. Denominator is the same, so I don't need to worry about that. I can ignore that. So A is -1, B is -2. My winner is B. And I could do that without showing you the equation by just saying, well, the distances are the same. We have a plus and minus in both cases. So the thing that's going to be the most negative is the thing with the biggest charges. So hopefully that little demonstration was helpful to you to figure out how to logic, if you can, how to logic your way through like multiple choice questions. Just eliminate one by one. All right, any questions whatsoever about any material we covered? And if you're typing that out, I'll just go through my normal spiel. Homework is, I'll put one up for this week. You should have 2 parts. Reading guide quiz on Monday, as always. Only one more test to go, and then the final exam. So if you're not doing so well, there is still time to make up your grade. Like test 4 is probably we have a lot of visual stuff going on, so it's probably the least math intensive of all of the tests. So that's a very good opportunity to score really good. And then the final is just everything you've seen already. And that's usually historically on my finals, people do way better on those than on the tests because all the material is more or less old. So don't be dispirited if you're sitting like in the 60s. There's still time to bump that up to a C, or if you're in the 70s, you can still bump that up to a B. You're still in the 80s, bump that up to an A. For the lowest drop test, I will be doing that maybe tomorrow. I just want to give people time to look at test 3, look at their scores. I'll put up the guide to how to do test 3 probably this afternoon. You can look at it maybe 1 to 2-ish, depending on if I have meetings set up. Otherwise, that's all I have for you. Take a well-earned break from chemistry for a day if you can, and then make sure to do your homework. Does the final fall? No, the final does not count into the lowest drop test. Like, I'm not going to drop your final. Your lowest drop tests are only tests 1, 2, 3, and 4. So even if you're doing really well in this class, you still have to take your final. All right, that's all I have for you. Everybody have a good weekend, and I will see everybody a little bit in the future. Take care, everybody.